So today we're going to discuss matrix operations. And so this is a continuation of the last class on Friday. So I want to just finish up some items that I did not get to at the end of last class. So there are three operations that we went through last time. One was matrix addition. So you just add matrices by adding them component-wise. So if you have A being equal to Aij, B being equal to Bij, then the sum, recall, you just take the corresponding components and you just add them together. Okay, so the second operation was the operation of scalar multiplication. And here, your scalar is a real number. And you take a scalar times a matrix with entries Aij. And what you do is you just multiply the scalar into every single entry. So this is lambda times Aij. Okay, so for example, if you have lambda times 1, 1, 2, 2, then this is going to be equal to lambda, lambda, 2 times lambda, 2 times lambda. Okay. And then finally, we use the dot product to talk about matrix multiplication. So if I have two matrices, so A is going to be an m by n matrix, and B is going to be an m by r matrix, then I could define the product A times B, and this is going to be an m by r matrix. And so the way we define matrix multiplication was as follows. So A times B is going to be equal to Cij, where Cij was obtained by taking the sum over all k of Aik and Bkj. Okay, so we matrix multiply by taking dot products between rows of A and columns of B. Okay, and we did several examples in class. So if you want to review that, you should review the notes from the class from before. All right, so we talked about transposes. I have to start off from there. So if you take the transpose of a matrix, so your matrix may not be square. So it's going to be an m by n matrix, and A will be Aij. Okay. So the way we transpose matrices is we interchange rows with columns. So let me do an example. So the transpose matrix is just going to be AJI here. Okay. So let's do an example. So if I take 1, 2, 3, 4, 5, 6, then the transpose, what we do is we take the first row of A and make it the first column of A transpose. So we have 1, 2, 3 here, and then we do the same thing with the second row of A, we make it the second column of A transpose. Okay, now with transposes, we have certain properties, and let me review some of the properties of the transpose. So the first property is that if I take A transpose, and if I transpose it again, well, it's pretty clear that what's going to happen is you get A back again. Okay. And then the second property is if you take A plus B, and if you take a transpose of that, then you're going to get A transpose plus B transpose. Okay. And if you take a scalar times A, and if I transpose that, that's the same thing as taking lambda times A transpose. Okay, you could just pull the scalar out from the transpose and it doesn't do anything. And finally, probably the most important property is if I take the product of AB and if I transpose this, and this takes a little bit of work to show, but it turns out to be a very nifty property to have. This is going to be the same as B transpose A transpose. Okay. All right, so what I like to do is I like to go over some problems and see if we can sort of apply some of the things that we've done in this class to actually solve these problems. Okay, so these are additional problems. Okay, so first problem. So let A be equal to the matrix 3 minus 4 minus 5 and 1. And B be equal to 7, 4, 5, and K. All right, so here's the problem. So what values of K are such that, so we want to find the values of K such that A times B is equal to B times A. Okay. So we'll matrix multiply on both sides and, we'll just compare. And once we compare these two, then we'll actually see what K has to be. All right. So let's multiply A times B first. Okay, so I'll put the matrices down here. That's 3 minus 4 minus 5, 1. And B is 7, 4, 5, and K. And I think I have enough room over here, so let's just do that. So I take the dot product of the first row of A with the first column of B. So it's 3 times 7, that's 21, times minus 4 times 5, so it's 21 minus 20, and that's a 1. Okay, then I take the first row of A with the second column of B, so that's 3 times 4, that's 12, times minus 4 times K. So it's 12 minus 4K. Okay. Now the next one, I'm going to take minus 5 times 7. So that's minus 35 plus 5. That's going to be a minus 30. Okay. And then finally, I get minus 5 times 4. That's minus 20 plus K. All right. So that's A times B. And now let's do B times A. So we just reverse the process. And here's what we get. So again, 7 times 3 is 21 minus 20. That's going to be a 1. The second one is minus 28 plus 4. That's minus 24. Okay. The next one is 15 minus 5k. And the last one is minus 20 plus k. All right. Okay, so the good thing is that these two are the same. So this one here matches with that one here. So any k is going to work. So what we have to do is we have to look at the entry right here, compare it with this one, and compare that one with that one. So for these two matrices to satisfy the commutation condition, I need 12 minus 4k to be equal to minus 24. Okay? So that means minus 4k has to be equal to minus 36. So k has to be 9 in that case. And notice that when I take minus 30 equals to 15 minus 5k, for k equals 9, this actually works out. Okay, because on the right-hand side, you get minus 45 plus 15, then that's minus 30. So the answer here is k equals 9. Okay. All right, second problem. Okay, so suppose that C times A is equal to the identity, the n by n matrix. Okay. So show that AX equals 0 has only the trivial solution. Okay. So this is going to lead into the topic of inverses. And the idea is an inverse is something where you can actually get sometime, if you start with something and you multiply it, you want to get 1. All right. So naturally what you want to do is to actually apply things which would give you 1 so that you can make things a lot simpler. Okay. So suppose we have AX equals 0. And ultimately, we want to show that X is actually equal to 0, because that means that we have the trivial solution. So what's the natural thing to do? Well, the natural thing to do is just multiply by C on both sides. So if you just take C times AX, that's equal to C times the 0 vector. And when you multiply any matrix times the 0 vector, you get just the 0 vector again. Okay. And as I mentioned before in the previous class, matrix multiplication is associative. So I can write this as C times A times X is the 0 vector. But C times A is the identity matrix. And so that means that X has to be 0, because identity matrix times any other matrix is actually equal to the matrix itself. It acts like 1. So that means that X has to be equal to 0. Okay, so this is the trivial solution. All right, so this finishes off the section on matrix operations. I will continue on with several other videos. And I'll try to make them short so that they're not too long to watch. And so thank you for your attention.